This is Rebecca Raphael, Lab M03 with my Lab 5 Motion of Falling Objects report. I made an observation of a falling lacrosse ball and a falling crumpled paper ball. The objectives of this lab were to compare the falling velocity of two different objects and model the effects of gravity and drag, identify the terminal velocity, which is due to drag force, and analyze the difference between drag to weight ratio. The main results of this lab were that air resistance causes the crumpled paper ball to fall slower than the lacrosse ball because drag force has a stronger effect on lighter objects. Drag is related to terminal velocity because drag force is proportional to the velocity, and also with a high drag, the forces will cancel out and the net force will equal 0, which will mean the object will fall at a constant velocity. Here's the clip of the lacrosse ball. I set the start frame at the beginning of its drop and ended it while it was still in the air. I set the origin of the coordinate system at the center of the ball and had the negative y direction aligned with the angle the ball was dropping. I also found the diameter of the ball online and set the calibration stick to 0.063 meters. Here's the clip of the paper ball. I set the start and stop frames and the axis the same way as I did for the lacrosse ball. I also measured the diameter of the paper ball and set the calibration stick to 0.13 meters. For both clips, I used the center of the ball as the average position point and marked it every frame. The time between frames was about 1/30th of a second, and the total time was about 0.37 seconds for both videos. To predict the motion to make the velocity and position update code, I used Newton's second law. The F-net of the falling objects was equal to the force of gravity plus the drag force. To model the drag, the principle F equals negative BV was used. It was also necessary to know that the force of drag is opposite to the direction of the object's motion and proportional to the object's speed. Here is my code. To predict the force gravity, I used the equation mass times gravity, and it was moving in the negative direction, so I made it negative. And to predict the drag force, I used the equation negative b times velocity times the magnitude of the velocity, where b was a constant. I ran it while t was less than 0.37 seconds, because that's how long my videos lasted, and plugged in the initial conditions of each ball. This is an example of my code modeling the motion with gravity and drag forces of the paper ball being dropped. As you can see, it begins accelerating, but due to the drag, the velocity becomes constant, so the line straightens out. The initial conditions of the lacrosse ball were I started t at 0 and ran until t equals 0.37. I set a delta t of 0.01 so it would be small compared to the total time. The mass was 0.14 kilograms and it started at 0.001 in the y direction and a velocity initial of 0. Here is the graph of the falling lacrosse ball compared to the model of force gravity only. As you can see, they are both exponential and the velocity is increasing as it falls. Here are the initial conditions of the paper ball. I started it at t equals 0 and ran it until t equaled 0.37 seconds. I set a delta t of 0.01 so it would be small compared to the total time. The mass was 0.004 kilograms and it started at negative 0.003 in the y direction and an initial velocity of 0 since it started at rest. Here is the graph of the falling paper ball compared to the model of force gravity only. As you can see, the model trend is exponential while the experiment trend has started to become linear. This is due to the effect of drag force, which will be shown in the next graphs. Here is the graph of the lacrosse ball compared to the model with drag. The comparison does not look much different than when only the effect of gravity was modeled due to the fact that the lacrosse ball is heavy and therefore drag does not have a large effect on it. On the other hand, here is the graph of the paper ball compared to the model with drag, and the model trend is much more accurate now with drag force because it starts to become linear like the experiment graph. The larger effect of drag is due to the light weight of the paper ball. So what does it mean? Here is a comparison to the graphs of the falling paper ball with and without drag. As you can see, the experiment model gets linear at the end. This is because the F-net equals 0, since the force of drag and gravity are canceling out, so the velocity is constant. This is why when drag is taken into account in the model, the trend also becomes linear and hits the terminal velocity, while in the top graph, where the force of drag is not taken into account, the model trend is exponential. What if the object was thrown downward and did not have an initial velocity of 0? Well, here's the graphs comparing the slow model, which was the paper ball, when it is modeled with and without drag. The terminal velocity is only reached when there is drag, but as it is shown by the top two graphs, it is reached much faster when there is an initial velocity compared to when it is starting from rest.